Alright, welcome back to these slides. Let's go and finish them up. So we learned about the magic of makefiles. It's a way to say, in just one file, give recipes for all the little intermediate steps and also the final step for the program you're trying to build. And then you can ask this beautiful make terminal command to give you whatever you wanted. You just ask for what you really wanted, and it can make all of the intermediate things that it needs to as it's going. So yeah, let's finally do it for that searching library that we came up with last time. So here, let's copy it in. Was that everything we did last time? Yeah. So everything.cpp to here, and then everything.h to here. Okay, so there's my library. we've got the main file that uses the library. We've got the header file for the library, and then also its implementation file. So all those three things together, we need to somehow compile, and we want to do it separately. So you only need to recompile the .cpp files. The header file is just being included automatically, so we're good with that one. And yeah, so let's go and make .o files out of these, and then link them together. We're going to make rules to do all that stuff. Okay. So yeah, let's make a make file, and it's going to look like this. It's going to have recipes for all the different pieces. Okay. So let's make that main executable as well. So I'm going to make a brand new file. Got all these things. I'm going to make a brand new file called just makefile with a capital M. That's how it needs to be. Okay, so now I'm in the makefile language. This is not C++ anymore. And just to drive that point home, it's a number sign for comments, just like in Python, not in like C++. So this is a makefile comment. I'm typing in this makefile language now. And so every rule for a makefile looks like this. It's always target, ingredients, and then you tab over and give as many lines as you need to build the target out of the ingredients. So every rule in a makefile looks like the following. It's always like, got the name of your target, colon, the different pieces you need, the different ingredients. Ingredient 1, ingredient 2, as many as you need, and then you tab over. Okay, you tab over, and like it will do it for you in Vim, I think, and also in Nano, but it's not spaces, it's actual tabs, and then you start giving all of the terminal commands to build, to make the target from the ingredients. And that's what you give there. Okay, so as many as you need to use these guys, assume you have them, to build the target, because it won't run the rule unless it has these ingredients. It will go looking for them if it does not have them, and hopefully there's a rule if it needs them. So yeah, let's make all these different rules for what we need. So we need object file rules for these guys. We need to make the .o files for main.o and searching.o. So let's do that one. So to make searching.o, for example, I need what needs to exist first, searching.cpp, better exist, otherwise I have no way. And then you press enter and it's automatically tabbing over for me. And then you say what you need to do to your ingredients to make your target. It's going to be a g++-c, right, on that original file, searching.cpp. So that's how I use searching.cpp to build searching.o. Does it all make sense? And then, same idea for main.o. If I want to create main.o, I better have main.cpp to exist, and then I'll use g++-c on that to build it. All right, so those are those two rules. And then finally, one more rule, right? We'll have one more to make the final executable file. Let's call it main this time. So its name, our target name will be main, and then what needs to exist in order to make main? We need all the .o files, main.o, searching.o. Okay? So given these, assuming that I have them, how do I use them to build the final executable called main? Well, I need to use g++ to link them this time, right? So give them to g++-o, call it main because that's the name of my target. All right, so those are the rules. That's how it needs to look, okay? And that's it. There's our makefile. We can use it now with the make terminal command. All right, and so here's how you use a makefile. You say, make is the name of a terminal command that will go look for the makefile and run the rule that you ask for. So you say make space the name of the target you want. So I'll say make space main.o, and you see that it ran the body of that rule. It's like, all right, yeah, I need that one. And there it goes, it made it. All right. And then if I say make space searching.o, if I could spell searching.o right, it will go run that rule. Now I have a searching.o. Like, you just set it once and you just use the make command to get what you really need. And then finally to make main, you say make main, that's the name of the target, and it links them together. And so I have a runnable program. Beautiful. It's working out. Okay? And that is the beauty of makefiles. And that, I did it in a weird way. Let's do it the right way now. So let's remove all the .o files and also the final executable main. So I'm back to just a blank slate. What you really do in a makefile is you say what you really want. Say make main. And even though those .o files don't exist anymore, I deleted them, it will notice that, okay, yeah, to make main, I need these guys. I need main.o, I need searching.o. They don't exist right now, so I'm going to go looking for a rule to make them. Like, oh, I found it. So it's okay. It says, I need this. I have this. Let me run that rule. You see it's making the main.o, making the searching.o, and then relinking, linking them all together to build the main executable. It does it all for you when you ask for what you really wanted. Isn't that beautiful? / main, and it all works. And also, makefiles that compile in the most efficient way. If it notices that there's nothing to be done, it tells you. It doesn't even try. It notices that the files didn't change since it last was compiled, and so it's just happy. It does not need to do anything else. Okay, so that's one nice thing. And then another nice thing is that if you just say make by itself, it'll run the first rule in the file. And so usually you put the rule you care most about up there at the top. So like, now I can just say make instead of make main. It will run that rule. Isn't that neat? And so what else do I want to do? Let's add a line. Let's change one of these CPP files. Let's be like, okay, instead of searching for 87, let's search for something else. Let's search for 42 now. So I've changed main.cpp. So what needs to be recompiled? I need to remake main.o and then relink it into main with the existing searching.o. Nothing needs to change. And makefiles know that. It will do it the most efficient way possible. So now if I just say make and hit enter, it's going to run this main rule and notice that, oh, main.o is out of date. I'll remake that. Searching.o was not out of date. I don't need to change anything there. And then it goes and it links with the final body of the real rule. So it only needed to remake main.o. Do you see that? And it figured that out. Do you see how that's going to save your life? It's going to make, and there's my new output, it's going to make everything in the most efficient way possible. And that is makefiles in a nutshell. All right? It's worth using, right? So once you make this, you can just use make all day long, and it will make your program for you however you need it to be made in the most efficient way. All right? Beautiful. All right, so now I want to switch gears to something different. Let's talk about complexity again. I promise to not test you very hard on this. I promise that if I test you on anything about complexity, it will be a very obvious answer. Okay? That is my gift to you, because complexity theory is more of a CSCI 41 topic, and we'll get to that in due time, all right, if you take my CSCI 41 or anybody else's. So yeah, let's talk about complexity and like how fast programs are compared to other programs. So remember this basic operations counting stuff? Let's do that for linear search and for binary search for these two implementations. So let's see, let's open them up. First, we got your linear search, and you got, and you got your binary search down here. That was a little bit more complicated, right? Hopefully you remember the algorithms, but let's count their basic steps. Let's figure this out together, okay? So remember that a basic operation is just something simple in code. It's like an assignment statement, and like a plus minus time, something arithmetic. Checking a condition takes one step of execution time in the processor. I'll call that a basic operation, all right? And it's usually just like one line of code corresponds to like one or a couple basic operations, assuming that that line did not call some other function that like itself did some weird loop, okay? So yeah, remember that counting up those basic operations tells us exactly how many steps of time it will take on a processor, and that's very helpful. All right, so just for review, let's say this line, int x equals, I don't know, 5 plus 2. Very simple line. So how many basic operations is this line? Think about it for a second. What's going on? You have one arithmetic thing. You need to create 7, and then you need to shove 7 somewhere into a variable. So it's 2 basic operations total. You see it? 2 basic ops. And so that's going going to take 2 steps of execution time in the CPU, all right, on any CPU, even the one in your laptop versus the one in your phone, even the one in your microwave, doesn't matter. So that's why we count basic operations. All right, so now the question is, how do we do that? How do we do that for linear search, for binary search? I think you can imagine that linear search, having a loop, runs differently depending on the size of the vector, doesn't it? So like, if you need to search through, in the worst case, you need to search through the entire vector, that's going to take a lot more time for a bigger vector, isn't it? So, all right, that's going to need a variable now. So usually when we're analyzing an algorithm, that algorithm tends to depend on the size of something. So we call that size n. It's like the size of the vector you're looking at, the size of the input that you're getting from the user. So we tend to use capital N to mean that. It's like n is the size of this vector, and that kind of controls how much work we're doing in a very real way. So with that in mind, let's count basic operations for linear search. This is just a screenshot of when I wrote it a while back. It's mostly what I wrote. So let's see, green even doesn't show up here. So let's count basic operations and figure this out together. All right, I guess I'll use the white. There, that shows up. Cool. So okay, basic operations for a for loop. We're gonna have to figure out how many times it repeats its body, but like at least this first one, that's only gonna happen once. How many basic operations in the int I equals 0? Just the one, right? To shove the 0 into an I variable. And then, let's see, we need to repeat then. It's always condition, body, increment a bunch of times. And so we'll have to figure out how many times, but let's just count individual basic operations now. So to get v.size, let's pretend that that's one basic operation to ask the vector for its size. I haven't really told that to you, but like it's going to return back a size. It's saved in memory. Just assume that's one basic operation. And then once you have it, you'll compare it with I. So that's 2 for the comparison. And then we run the body and the increment. So what's the body doing? Well, it's got to go somewhere. It's got to get a value out of a vector. So that's 1. And then once it has it, it will compare it. That's another. And then finally, it will eventually return. We'll just count that. We're going to do an upper bound for the limit of the basic operations. So that's the body, 3 basic operations, worst case. And then we do I++. Remember that that's secretly I equals I plus 1. So in addition to a plus, it's also an assignment. So 2 basic operations there. And then that repeats. And then there's also this return statement down here to give back a value from a function. Let's pretend that that takes 1 basic operation. All right. So yeah, it's like these guys plus however many times this stuff is repeated. All right. So we got to figure that out. If you stare at the code for long enough, you see that I is going to range from 0 to size minus 1. That's size times. Let's give the variable though. Let's say that v.size that's our n, our capital N, as we're analyzing. And then, all right, let's start counting stuff. So that like the start of the loop, the initialization of the loop, that's going to take 1 basic operation. And then we have to worry about this loop. So what's it going to do? It's going to loop. How many times will it run the body? Well, from 0 to size minus 1, that's n times total, won't it be? So it's going to do condition, body, increment, n times. And that's how many operations? 1, 2, 3, 4, 5, 6, 7. So n times, it's going to do 7 operations. I hope you see that. Do n times 7 ops. And then, to stop the loop, remember that we have to test the condition one last time. Now I is too big, it's equal to size. We don't want to do anything anymore. But we have to notice that to stop the loop. So this condition needs to fail, which requires us to check it one last time and notice that it's false. So that's 2 more basic operations. The condition runs once more to get us out of there. So 2 operations for that one. And then finally, if we get down here in the worst case, there's 1 more to return. All right. I know that this is like an overshoot at what it really is, because like we're always going to only return once. Like we shouldn't be counting that as 3. That's kind of silly. But for the body, 3 operations, but that's okay. We're going to do an upper bound. That's good enough. Okay. And so with that, in total, what we got? 1, 2, 3, 4 plus 7 times n. So add it all up. 4 plus 7n basic operations, given the size of your vector is n. And that makes a lot of sense, right? Now we know, it's very clear that if we have a bigger vector, the amount of time it's going to take gets even bigger. You see it? That makes a lot of sense. So It's like the graph of a line. That's another reason maybe why it's called linear search. Okay, so that's the analysis for linear search. Please yell at me if you have any questions about this stuff. It's fun for me to explain, but I can understand if it takes a while to sink in. Next, I want to do binary search. All right, so definitely go study this until you get it, and then ask me lots of questions. And now let's do binary search. Okay, so let's count the basic operations. I'll just do this quicker. So this guy, there's one, get the size, subtract, set it to a variable, that's 3. And then this loop, condition is just one basic operation. You got the things in variables already. So we'll repeat this body some number of times, we'll figure that out. And then let me just start drawing arrows. So that's another basic operation, a third to assign, one to go into a vector, one to do the less than, a plus, and assign, go into the vector, less than, subtraction, equals to, one to return the dang thing, and then, what else? I think that's all for the body there. And then finally, we got a -1, all right? So in the worst case, we're going to get to all of these. It's just it's an overshoot, it's an upper bound, okay? So I think that was all the arrows that I wanted to draw. Let me just double check my notes. Yeah, it's a lot of arrows. And so, all right, let's start counting. So on the outside, these guys, before the loop, we got 4 basic operations. 4 basic operations there. And then inside the loop, we're going to have to repeat a certain number of times. We're not sure how many. It's like do blank times. We'll figure that out. It's always condition body, right? As long as it's true. So condition body, adding all that up and doing it a certain number of times that we're not sure of yet. We'll figure it out together. Is going to be what? Well, there's one there. Let me section it off for a second. Let me start counting. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. I think it's 13. All right. Condition plus the body is 13 operations, as far as I can count. 13 ops. And then we need one more run of the condition to make it false, right? To just notice that we're done. So one more for the condition, because it takes one basic operation for that. And then, worst case, we're down here and we're returning -1. It's another one basic operation to do that and do the returning. Okay? So now the question is, what in the world do we put here? How many times is this loop going to run its body? And this is complicated, all right? So it's not obvious. Like, when do we know that we're done? We're done if we stop, if we find it. Let's just pretend we're in the worst case so we don't find it. And so the question is, like, how many times do I run the body? How many times can I possibly have a valid search space? Because that's what's controlling this body. As long as the search space is valid, I keep running. And so we got low and high, and they always change, right? We're halving the search space. We're cutting it in half each time. And so that turns the question into being, how many times can I cut that search space in half and still have something there? It's like you start off with the whole thing, size and search space. You guess in the middle, right? Do your checks. And then you pick a side, right? You still have a search space, you go down this side, go in the middle. And you pick another side, right? Maybe that was too big, so you're going to go to the left side. Guess in the middle of that. You're going to keep on cutting off half, right? And you keep on running the body as long as you have something to look at, as long as you have a valid search space to cut half off of again, right? Worst case, you don't find it. It takes a while. The question now is, how many times can you cut your size in half and still have something to look at, still have a valid search space? And so the question is, because it's getting smaller twice as fast, the question involves a logarithm. Does that make sense? Because that's the opposite of like the exponential. Like if you think of it backwards, it's exponentially growing twice as big each time. So the opposite of that, the inverse of an exponential function, is a logarithm. Does that make sense? And so you'll just round this up because it will probably have decimals, but you want the log base 2 of the size of your vector. That's going to tell you, if you round it up at least, how many times you can cut in half your vector and still have a search space to look through. There's still at least one thing there to go and look inside of. Does that make sense? So that's where the logarithm comes out, and now we can do our addition. All right, so this is going to be what, 6 times 13 log base 2 of n? Or 6 plus 13 log base 2 of n, the size of our vector. And that's the analysis. So it looks like the graph of a logarithm. As n gets larger, it like grows like that. Interesting. Compare that to the other one. All right, now we need to do the comparison. All right, so in general, no matter what these things were, because like what we solved for linear search, it was like something plus some constant plus a constant times n for linear search, and then a constant plus a constant time log base 2 of n for binary search. I claim that it doesn't even matter what those constants were. Log base 2 of anything of n is always smaller than n, even if those constants were really tiny, really big for the log base 2. Even if this was like, we know this was 13 for us, and this was like 7 here. Even if, let's see, even if this c right here was like 1 million, I claim, and this one was like 1 or something. Even so, like if you zoom out far enough, here's the logarithm, here's the linear thing, even if this is 1 million on the constant, you will still be able to zoom out and see this. Logarithm is always going to end up smaller in the long run. Does that make sense to us? It's just a slower growing function. So even if you had a large constant out here, you could zoom out far enough. Eventually, the linear search would get even bigger, even if it had a tiny constant. Logarithm just grows much more slowly, significantly more slowly. Does that make sense to us? And so it was 13 versus 7 in real life, but it really doesn't matter, all right? No matter what, for large n, this will always end up smaller than this, regardless of what those constants were. That's what I'm trying to say, all right? So now we can graph them both together. The linear search analysis versus the binary search analysis. So here's n, our variable down here, and it's always a function that takes the number n, how big the vector is, and gives us how many basic operations it took to run our algorithm. So linear search was like 7n plus something, plus 4. And so this is kind of like the graph of linear search, how much time it's going to take for a given n. Like for smaller n, it's going to do less work. For larger n, it needs to look through a bigger vector in the worst case. So here's linear search. And then for logarithm, even though this was bigger, right? Started off with 6, it was 13. This was 4 and 7, it was smaller on both ends for both constants. Even so, maybe for a little while, linear search wins out, but there will be a tipping point, just due to the way that binary search grows, due to the way that logarithms work out. All right, there will be a point at which binary search wins off. All right, it wins compared to it. Binary search, because that's what a log graph looks like, and so it's going to be better in the end. Once you get to large n, way over here, large n, which is usually what we care about for our algorithms. Like, if we do this in a giant data center, what's the algorithm to use? For sure it's going to be binary search, because it's going to be ridiculously a lot more work compared to linear search as n gets huge, like millions sizes is a billion or something. All right, maybe for like the first 10 or 15, binary search isn't that bad, or it's a little bit worse than linear search, but like once your n gets large, it's no contest anymore. Does that make sense to us? And that's the reason we do this kind of analysis. All right, this is going to work out. Okay, I think that is what I wanted to say there. Yeah, that's the reason we do this analysis, just to notice that. It's like, all right, yeah, I always want to use binary search if I can, because it's gonna just like blow linear search out of the water. There's no contest. Okay, so as n gets large, for sure binary search is the one to use if we can, if it's sorted. And yeah, that leads us to a kind of notation, because we just noticed, like, no matter what, if you zoom out far enough, these constants didn't matter at all. It's just, it turned into a battle between log base 2 of n and n itself. Those constants didn't really matter if you zoom out and you look at large n, which we usually do in computer science. So we made up a notation for that. It's called big O notation, all right? And it's just a way of simplifying your analysis to like get out the thing that was interesting, the important stuff. It was the log n here that was important. It was the n here that was important. These constants weren't, okay? And so here's the rules of putting a analysis into big O notation. This is something you're going to get very familiar with in CSCI 41. We noticed that our analysis was like 7n plus 4 for linear search. To turn this into big O notation, you take nothing but the highest order term and cross everything else off, like what's going to grow the fastest as n gets large. As n becomes 1 million, this plus 4 is doing not much at all. So you'd cross off the plus 4, turn it into just 7n. Okay? That's what you do. And then you drop off any constant multiples out in front, because you don't really care about like 7n versus 8n. You care about log n versus n. Like that's where you get a real big payout, all right? That's where you compare against. And so even this constant doesn't really matter as n gets large when you're comparing against different kinds of functions. So you just turn that all into, like, this turns into that, turns into just n. Like, that's the answer, all right? And then you tack an O at the front, and you put this between parentheses. And so what you end up saying is linear search, if I can write in a legible way, we say that linear search is big O of n, okay? That's how you write it. That's how the analysis works. And that's just a shorthand. It's showing you what you care about. Like, n is what matters here compared to, like, log base 2 of n. Okay? It's something invented by mathematicians to talk about function growth, and it works here for computer science. Talks about just in general how fast is something going to grow compared to other things. And so we love to use it for algorithms because that's where we come up with a notation. That's where we come up with a formula for how fast our program's going to take to run. Okay? And so this is a typo. We ended up with 7n plus 4 this semester. Sometimes I mess up, apparently. And so we turn that into, not 7n plus n, 7n plus 4. We turn that into 7n only, because we got rid of the plus 4, because as n gets large, that plus 4 is just a drop in the bucket. It's nothing huge, nothing important. And then also, because we're going to compare this to, like, other functions that, like, are n squareds and log base 2 of n's, this 7 wasn't really doing much when you zoom out and compare it against those other kinds of functions. And so we turn this into just n by itself. All right, and we say that linear search is big O of n, and you write it like this, big O of n. That's how you read it, all right? Another word for big O of n is called linear time, because the graph of this looks like a straight line, okay? So we call that linear time, big O of n, and you'll get very, very acquainted with this in CSCI 41 if you wait until then, all right? There's also stuff in your book about it. And what was the next one? For this one, it was 6, 13n plus 6. Apparently I did it wrong last time too. There we go. So binary search, we came up with this. It was 13 log base 2 of n plus 6. So to do big O, we drop the lowest order terms. We keep just this one, right? That's the one that's going to grow the fastest. The plus 6 doesn't matter as n gets large. And then also this 13, any constant out in front, we chop off, because if you compare it to n, like, and you zoom out, the constants out in front don't matter. Like, log n is always going to win compared to n, no matter what was out in front. So you just turn that into log base 2 of n, and then we say that binary search is big O of log base 2 of n. That's our analysis. All right, we kind of, like, crossed off some stuff. This is just like the meat, the main detail about how fast the algorithm grows, all right, as n gets large. And then another word for big O of log base 2 of n is called logarithmic time, because it's the graph of a logarithm, as you would expect. All right, so yeah, I think that's what I wanted to say there. And so this is a very good kind of analysis that everybody uses. You will be forced to learn it, all right? You're seeing a little bit of it now, all right? This will be hit hard in CSCI 41. Sometimes you do want to, like, get out a timer, a stopwatch, and keep track of how long it takes your program to run on your specific machine. Like, that is sometimes important. And so there's a way to make a little stopwatch in code. It's using the ctime library. In the ctime library, there's like a clock function. There's a clock function that you can call, and that just kind of looks at the clock inside of the CPU. Where's that? Ctime clock. It gives you back a weird type. It's called clock t, and that's just the type of the clock inside the CPU. It's just an integer value, a big number. And then if you call that twice, like the first time to look at it before you do your algorithm, the next time after you do your algorithm, you run your algorithm in between, then you can just, like, subtract the time from each other. And then to turn that into seconds, you divide by a constant in the library called clocks per sec. And because clock t is an integral type, if you do division, normally it will chop off the decimal places and do integer division. So you need to make one side a double to get seconds with decimal places in it, and that will convert and give you back the time elapsed for your algorithm in between here in seconds. Okay? So yeah, that's something that you may need to do one day, but in general, we care more about big O notation. Like, that's the real analysis that we like to do as computer scientists. All right. Yeah, there's one last thing I want to talk about now today. It is sorting algorithms, okay? Again, my promise to you, this is usually a topic that you hit hard in CSCI 41 again, and then you analyze all the sorting algorithms. So I promise if I give you any questions about this, it will be very obvious and simple, all right, on a test. So yeah, that's my promise to you. And now let's talk about sorting, how to sort numbers. It's just like we have something that's jumbled, we want to make it in order. You've seen the sort function. Let's talk about how it was made. So Okay, I want you to think of an algorithm. Before I show you, there's a bunch of different competing algorithms for sorting. Before I show you any of them, I want you to think about it. Pretend that I type a bunch of numbers on the whiteboard. A bunch of papers, like a bunch of sticky notes in this order, let's say. 18, then 23, then 12. That's an order. It's like a vector. All right? I tape a bunch of these, or I give you a bunch of index cards and put them on the desk in front of you. What would you do? How would you shuffle them around? Like, what would be your strategy to, as efficiently as possible, sort these numbers? Get them into order where like 7's first, then 8, then 11, right? How would you do that? How would you sort that list? How would you rearrange the sticky notes on the whiteboard? Pause the video and think about that. Do you have your answer? So, I claim that whatever you chose, most likely it was an algorithm either called selection sort or insertion sort. All right? So I don't know about you guys, but what I would do if I saw this is I would just go looking for the smallest one, be like 7. Put that first. Then go looking for the next smallest one, 8. Put that second. And that's called selection sort. That's an algorithm that sorts, finding the smallest thing, the next smallest thing. There's another algorithm called insertion sort. That's usually what you do when you have like an Uno card hand, like you're trying, or like you're playing poker or something. Like you're sorting cards in your in your hand, and you start like moving them over. Like, all right, the 12 needs to go there, the 8 needs to go even smaller, the 7 needs to go there. You just kind of like bring in a new one, put it where it belongs as you like draw another card. That's called insertion sort. And so let me tell you in detail and give you code about how both of these are made. All right, but to get there, let's do the simplest possible sorting algorithm. It's called bubble sort. It's very dumb. It's not good at anything, but it's the first algorithm that we tend to learn because it's the simplest to talk about. It is not at all efficient, but at least it's easy to talk about. All right, so there are a bunch of cool websites that have animations to describe all these sorting algorithms, and so I want to show that to you. Okay, so here is, let me zoom in. And what this is an algorithm visualization website, and there's a bunch of buttons. At the start, you can click all the sorting algorithms. This first button shuffles an array, makes a bunch of random things in an array, and so here are the real numbers in the array in that order down there. But it's also showing you with bars how like relatively big that number is compared to the other numbers in the array. And so after these algorithms are complete, I'll click bubble sort and it will do the sorting algorithm. You'll watch it work. After it's done, you should expect to see a just steadily increasing line of bars there, right? Because the bigger things will be on the right, the smaller things will be on the left. So look for that, okay? But let's talk about bubble sort first. So just in general, like the job of a sorting algorithm is to take a jumbled vector or a jumbled array, 8, 6, 7, 5, 3, let's say, and to turn it in to a sorted, usually ascending order, sorted vector or array. So this will turn into 3, 5, 6, 7, 8. All right. And then the way that you get there depends on the algorithm. So what bubble sort does, here's pseudocode for bubble sort. It's not quite correct C++, but you can kind of read it. You can turn it into C++ very simply. What bubble sort will do is it's just going to go through the array and start swapping elements that are right next to each other. It's just going to look at things right next to each other, right in between, and see if they're out of order. If they are out of order, it will swap them. If they aren't, it will keep them in order. All right, so here's what bubble sort's going to do. Don't look at the code just yet. I'll try to walk you through it. Or try to see how this is going to work out in the real code. So like if this was my vector, 8, 6, 7, 5, 3, what bubble sort will do is it's going to look at these two elements that are all right next to each other, the 8 and the 6, let's say. And it's going to say, are they out of order? And yes, they are. So it will swap them, 6 and 8. All right, that's what it's going to do. And it's just going to do that a bunch. So this is what it's doing. Like, look at these numbers, 1 and 1 right after each other. If they're out of order, like the next one, the one that came first was bigger, swap them. Here's the standard swapping code. It's going to keep doing that. Then it zooms over here. See it? Now it's 7 versus 8. Are they out of order? Yes. So it'll swap. 7, 8. Okay? Now it's 8 versus 5. Are they out of order? Yes. So it will swap them. Now this is 5, this is 8. And then one more time. Oh no, now I can't move it separately. And then the very last, on the end there, it's 8 versus 3. Are they out of order? Yes. So it'll swap them. 3 goes here, 8 goes there. And then it made its way through the array once, and it's still not in the right order, though, is it? The only thing that is in the right order is this 8. The biggest thing after you go through the array once will end up being pushed to the right, just due to the way that math works, right? So this is now fixed. You need to do the process all over again for this one smaller vector now. Okay, does that kind of make sense? Now it's like, all right, 6 versus 7, they're in the right order. I'll just keep them as they are, even though that's not where they should be. And now it's 7 versus 5. Are they out of order? Yes. So it'll swap. Now this is 5. This is 7. It's getting closer. After every round, it's going to move the biggest thing into the right spot, though. Now it's 7 versus 3. The 3 belongs to the very left, but it's not going to do that. It's going to swap these, 3 and 7. Like the 3 is slowly making its way over to the left. Does that kind of make sense? And now I'm done with this. Like the 7's in the right spot. I'll just consider this vector. I'll go through that and do the same game until it's all over. So you have to keep on going through the vector. It gets smaller and smaller, like the stuff that you need to go through each time. But more or less, you're going through the entire vector each time. Does that make sense? So it's like a doubly nested loop. I hope you see that. So in general, you're going to have to go through this vector size minus 1 times, right? In the worst case, you're going to have to do that many runs through the array, because like it gets smaller and smaller and smaller. How many times until you're done? Size minus 1 times. And then how do you go through that entire array, that subarray that you're working on right now? It's another loop. See it? That's what J is going through. It's like J starts from 0 up to like the edge of where I am right now. It's always minus I minus 1. See that? So yeah, and then it's going to go and compare the things that are right next to each other and swap them if they're out of order. All right. So it's always, for a given round of that inner loop, it's just like the next biggest element will always win out. Like the 8 gets in the right spot, then the 7 gets in the right spot. So it's moving the bigger things over very quickly, and then the smaller things over very slowly. Like the 3 after 2 rounds moved over twice. So it needs, in the worst case, we need to go all the way. We need to go this many exact times to move the 3 where it belongs. Okay? So yeah, this is in a roundabout way. Let's show it first, and then we'll talk about its analysis. So let's click bubble sort. You'll watch it highlight the things that it's considering right now, and it will swap them if they're out of order. Whee, look at them go. It's swapping them if they're out of order, swapping them if they're out of order. You see it doing it? And that is way too slow for me, so I'm going to change the speed to as fast as humanly possible. And you see it, like the bigger things, they're moving over. They're moving over. And the smaller things, they're just moving over by 1, because that's how swapping works. This is very naive, right? It's very, what's the word? Myopic, I think, right? It's short-sighted. It's not really looking at the big picture. It's just looking at things that are right next to each other. It's not very helpful for this. But I mean, it's going to get the job done. I think you can kind of see, like, it's for sure going to sort the thing, just not in the most efficient way. And man, does it take a while. So it's swapping, it's swapping, it's swapping. It's moving bigger things over quickly, and smaller things just move by 1. But it has less and less work to do each round, because it's like this right side of this vector, it's happy. It's not changing anymore. So it's slightly faster because it has slightly smaller subarrays to go through now. But like this guy, this number 11 here, it's going to move way over to the second element. And now it's done. All right? So that's a bubble sort. That's how it works. And I hope you see it. And so in general, though the array size does get smaller each time, just like hand wavy, this is going through the size of the vector, and this is going through the size of the vector, and nested loops multiply work. This is constant work, like some number of things, like 10 basic operations or something. And so it's going to be n squared. It's big O of n squared. And that's the analysis, more or less, okay? And we think that is very slow. N squared is pretty slow when it comes to the world of sorting, and bubble sort is the slowest. It has the worst constant out in front of that n squared, because you know that big O throws away constants. There are other n squared algorithms that are still faster because they're just like not thinking about things right next to each other. It's thinking about the big picture. Like that will save us time, right? But that's bubble sort. That's the simplest one to talk about. Let's next talk about selection sort. So the selection sort is all about finding the current minimum. All right, so this is how selection sort is going to do its sorting. This is still an n squared algorithm, by the way. It's just a faster n squared algorithm. 8, 6, 7, 5, 3. And so what selection sort is going to do is it's going to, at the start, it's going to figure out like, all right, I got to find the smallest thing, and that's going to go in at the start. So it finds the 3, and it puts the 3 at the beginning. And then it doesn't need to ever touch this index again. Now it just needs to sort the rest of this array. See it? So now it goes through the rest of this array, finds the smallest thing. That's the 5. It'll swap it with the start, 5, 6. And now the 5's in the right spot. Then it'll go through the rest of this array. Find the smallest thing, put it at this index that it's trying to fill. Does that make sense? So it's selecting the minimum. That's what selection sort is all about. It tries to, in the code at least, it's like index I is the location you're trying to fill right now. And you got to go from there, like one after that, to the end of the vector. That's always where you're looking. From where your current index is that you're trying to fill right now to the end of the vector. Go and find the smallest thing, saving the index of the smallest thing. So it's going through the entire thing, find the smallest thing, and then swapping the value at the current index you're trying to fill with the value at the smallest index where you found the thing. Okay? That's the secret. So it's selecting the minimum each time, and for the same reason as bubble sort, like this is going through the whole thing, this on average is going through the whole thing, so that it multiplies together to be n squared again. N squared, but significantly faster than bubble sort, all right? Even though when n gets large, it doesn't really matter. It's still very, very slow comparatively to better sorting algorithms, but I think it's better than bubble sort because like it's doing less work in the body. It doesn't have to move things over as much, okay? So it's like in one fell swoop, it's finding the smallest thing, okay? So yeah, less swapping involved. It is better than bubble sort. It will be faster, but selecting the minimum, it is still n squared though, because it has to do that selection, go through the entire vector, which is a linear process. It has to do that n times, so n squared. So selection sort, you'll see it highlight its best guess for the minimum, and then by the end, once it's finished its round, it's going to put it at the start, and then it never touches that index again. Now that's in the sorted order. Now it's figuring out the rest. And so it's still pretty slow, but it's faster than bubble sort. Still n squared. So it's selecting that minimum. Do you see it? Getting there. That was kind of backwards compared to bubble sort, right? Because it's making the smaller things on the left versus the bigger things on the right. But still, less swapping to be done. And beautiful. Now it's finished. That's selection sort. One more n squared algorithm is called insertion sort. All right, that was the one with like cards that I was talking about. Insertion sort is still n squared, but it does things a little bit differently. It doesn't like go and find the minimum. It keeps track of, we call it a locally sorted subarray. All right, and so here's my example. Let's draw what insertion sort's about to do. What it does is like, what I mean by locally sorted is like if it's sorted up to here, let's say, it sorts up to a given spot. And if it's done that, it's going to put the original values in sorted order. I'll show you that. But it's not going to like bring in the 3 because the 3 is way over there. It's going to sort the original values in those first 3 positions if we say that it's sorted up to there. All right. So it's not bringing in new things. And that's what insertion sort is all about. And so it has like what it calls a frontier. And so at the beginning, it has a left side and a right side. At the beginning, like the left side is sorted because there's only one thing in it. And then it expands its frontier by 1. Now it's like, all right, I'm going to bring in the next value, the 6. And then, all right, the 6 needs to move down to where it belongs compared to the 8. So the 6 will move down, be swapped with the 8. 6, 8 now. And so now it's sorted the first 2 elements in the original array. Those are in order. Does that make sense? That's the difference between insertion sort and selection sort. And then now it expands its frontier again, all right? It's got a locally sorted size 2 array. Let's bring in a third thing. Now it brings in the 7. It's like, all right, 7's new. Let's bring it down to where it belongs. So it needs to go down between the 6 and the 7, or 6 and the 8. So now this is 7, this is 8. And now again, the first 3 elements are sorted of the original vector. Does that make sense? And then it will expand its frontier one more time, bring the 5 down all the way to the start. I think you can imagine what's going to happen there. So that's how it works. It brings in a new thing down to where it belongs each time. It expands its frontier. Okay? So hopefully you can see that. So here's like where the frontier is. Starts at index 1 because like size 0 is already, or size 1 array is already sorted, like that one. And then it brings in the next one. So it looks at the next index, and then it keeps on, like that's the new thing, the index of the new thing, and it keeps on moving it down until it's in the right spot. So until it hits like the edge of the vector, or the thing before it is bigger, then it needs to swap it, kind of like bubble sort. It's going to move it on down. It's going to do the swapping, and this is a nice case of a while loop instead of a for loop, right? Just like while that new thing is too big, keep on moving it down. Like when we bring in the 5, it's going to be swapped with like, going to have to swap it over with the 8, with the 7, with the 6. Like they're all going to move that way. They're all going to move that way, that way, that way. and then there's room for the 5. I hope that makes sense. So yeah, that's what's going to happen. And the worst case in general, on average, it's going to be n squared. So let's run it, insertion sort. But it has a different best case analysis, and I'll show that to you once this one finishes. But you see, like, it's sorting. It's like ascending order, but like the rest of this, the right side of the array has not been touched. And so it brings in the new thing, expands its frontier, brings it down to where it belongs, and then it's done. Brings it down to where it belongs, then it's done. Goes to the next one. Brings it down. Some of them don't have to move down too far because they're already pretty big. Like this next one. See, it didn't have to move very much. But these small ones, you got to move pretty far. Like it's moving it down, moving it down. Almost finished. And people tend to agree that insertion sort is the best n squared algorithm because it has a better best case. In the best case, if everything's just slightly jumbled, not too far out of order, it only needs to move things down until they're in the right spot. If they're already close to sorted or already sorted, then you don't need to move them down very far. You only need to move them down a constant number of times. And then it's like a constant number times n. Then it becomes O of n. So let me rerun it. I'm going to re-click insertion sort. And it's just going to like expand its frontier, look and see if it's in the right spot. And it's like, yeah, it is. Done. It's already sorted. And if they were slightly sorted, slightly out of order, then it would still be pretty fast because it only needs to move things a constant number of places rather than like to the other edge of the array. So I hope you see that. That's insertion sort. And those are the 3 n squared algorithms. Everybody agrees that insertion sort is the best n squared algorithm because it has a better best case. So people prefer that one. But it's probably the most unintuitive, though. That's why we talked about it last. To get to better sorting algorithms, you can do better than n squared in general, even in the worst case. To get to those, we need to think about recursion. I'm so sorry, but the best sorting algorithms are recursive. That's another reason to learn recursion, okay? The best sorting algorithms have a property that's called divide and conquer, all right? It's very powerful, sounds cool. So they're divide and conquer algorithms, and here's what it means to be a divide and conquer algorithm. It's one that is first recursive, and then also it's recursing down on 2 halves usually of the problem. Like you split your problem in half evenly or into thirds, whatever, and those problems don't overlap. All right, that's the beauty of divide and conquer. You're going to break it down into those smaller pieces, and those smaller pieces you never need to look at them again. All right, like it's just going to break down easily, and then you build up the answer using the results of those smaller pieces that did not overlap. All right, so here's kind of like an example sorting algorithm. This is actually a real sorting algorithm that I'll get to on the next slide. So let's say this is our vector. A divide and conquer sorting algorithm will do something like this. It's like going to split the array in half, the left side and the right side, and it will go and recursively sort those smaller things. It's smaller, so you get to assume that the recursion does the right thing, right? This will be magically turned into 6, 7, 8. This will be magically turned into 0, 3, 5. You got to believe in the magic of recursion. It's like it's a smaller thing. Assume it's going to sort. And then you got these 2 guys. How do you build up the final sorted thing? It's just like go through them, iterate through the both of them, and pick out the right thing. It's like 0 versus the 6, because it's always like the smaller things on the left. So like, all right, the 0, 3 versus the 6, 3, 5 versus the 6, 5, and then you bring in the rest, 6, 7, 8. So that's a fast process. Once the 2 sides are sorted, you just kind of bring them back. And yeah, that's a sorting algorithm that is recursive and divide and conquer. That's called merge sort, the one I just showed you. It's called merge sort. So it's got 2 things. It's got the main merge sort function that does the recursion, and then it has a helper function called merge that merges back 2 smaller arrays that have been pre-sorted. Okay? So let me show you what merge sort is. Again, it's that same idea. Exactly what I drew was an example of an algorithm called merge sort. All right, so it's going to split it in half, make 2 smaller subarrays, and then go and recursively sort them. So it's going to turn it into, give the first call to the recursion, we'll give back 6, 7, 8, and then 0, 3, 5. So you called merge sort on these smaller things. You got back these 2 smaller arrays that have been sorted just by the magic of recursion. And then your job, after you do that, is to use those 2 smaller things and bring them back together. Merge them back, and that's why we have a helper function called merge. And merge is a linear process. It just needs to go through both of these just once, because they're already in order. Just like you need to bring them back down here. You do need to make some extra space for merge sort. You need an extra copy. And then it's like, all right, the first thing, what's going to fill in here? It's just always like you put a pointer at the start of this and the start of this, and like you compare. 0 versus the 6. 0 smaller. All right, 3 versus the 6. 3 smaller. See how you never need to look at those other ones again? 5 versus the 6. 5 smaller. And then once you've exhausted one, you just take the rest of the other. It's like, all right, then bring in the 6, then the 7, then the 8. Does that make sense? So yeah, that's how that will work. And that's a linear time process to do the merging after you've sorted. And so the running time, I guess first of all, you do need a separate array. Like this place where you're merging back to cannot be the same vector. Just try to merge these two in place, and you'll see the problem. But you do need some extra memory to do merge sort, but you do get more speed out of the deal. Instead of n squared, it's n log n. You've replaced an n with a log base 2 of n. And the reason you can do that replacing is because it's cutting it in half. How many times can you cut this thing in half? Like, you can imagine the recursion is going to cut these in half as well. It's going to break it down into some way. Break this down in some way. How many times can you cut something in half and still have something left to do sorting on? Log base 2 of n times, you better believe it. And so yeah, log base 2 of n times n turns into the running time analysis. Read about that in your book if you'd like. I'd be happy to explain more, but that's all that I really want to say. Merge sort in a nutshell. You'll study it more in a future class. But that's what merge sort is all about. It divides, conquers, and recombines. Beautiful. And so here is randomize. Here's a job of merge sort. Let me show that to you. You'll see on the bottom where it makes its copy. It'll have a second array being shown for a split second, and that's the copy of the array that it's trying to sort. Right now, it's merging back into some extra memory down there. So here it goes. So it's highlighting the parts that it's recursing on. You see it merging, like the stuff that's there, merging those back. Now it's recursively worrying about the right side, splitting it down, merging them back. There it goes, merging, merging. Now it's got 2 sides to merge. Done. I hope that made enough sense. So yeah, that's something to read about. It's a fun algorithm, and it finished before I could even finish explaining it. That's how much faster it is. N log n versus n squared. Beautiful. All right, so that's merge sort. And then the final one is probably the best sorting algorithm. It's called quick sort. It's quick sort for a reason. It is the quickest one. It is still n log n. On average, it's n log n, and usually it is. But this one's harder to explain, so I'm just going to use words, no code, a short diagram at least. Quick sort is weird. It is the fastest one, usually, on average, compared even to merge sort, but it's the hardest to explain for us. So that's why I'm talking about it last. Let's pretend that this is my jumbled vector or array that I'm trying to sort, and I'm going to give it to this thing called quicksort. So just like merge sort had a helper function called merge, quicksort has a helper function called partition, and that actually runs first before you recurse. So what partition does, when you say partition, it picks an element of the array and it calls that its pivot. It's going to pivot the array around that element that it chooses. All right? It's going to shuffle things around so that everything on the left side of the array is less than the pivot and everything on the right side of the array is bigger than the pivot. All right? So let me show that to you. So let's say that we call partition. That's the first thing that's going to happen in quicksort. We're going to call partition on this entire array. And let's just say for the sake of example that we choose the 5 to be our pivot element. All right? So what it's going to do is it's just going to put like a pointer on the left side and on the right side, and it's just going to start swapping in. It's like, all right, 8 versus 4, are those on the right side of the array relative to this pivot of 5? And you'll see like, no, absolutely not. The 8 should be on the right, and the 4 should be on the left. I'm trying to put things that are smaller than the pivot on the left, things that are bigger than the pivot on the right. So those two guys need to swap. So it works from the edges. So the 4 needs to go here, the 8 needs to go here, then it brings them in until it finds 2 more things that are out of order. So like the 0 needs to move to the left, the 7 needs to be on the right side. So it'll swap them. 0 here, 7 here, then it'll move them in. And whenever they meet, more or less, that means you're done. All right? So that means you're finished. And then you figure out like which side does this need to be on, right? Once they meet, then you're kind of finished with either like they meet on the left side or the right side, just depending on what this number is. And so notice how, though, like wherever they meet, that's going to give you a dividing line. That's going to give you a dividing line to tell you like where the pivot belongs. Like where they meet, That's where the 5 should be in the final sorted thing. Do you see that? So that's it. The last thing it does is swap those. That's what it does. After partitioning, that pivot is placed in the correct spot. And it never needs to move anymore. 5 is now in the right spot. So you can swap it with the 3. So there's a little bit more details there, but that's more or less the way it works. And now 5 for sure is in the right spot. Now you just need to work on sorting this smaller array and this smaller array. Does that make sense? That's what needs to happen now. And so these are smaller things, smaller arrays that you can then recursively call quicksort on. That's what it does. That's how quicksort works. It first picks a pivot. Usually randomly is the best way to pick a pivot. It partitions with respect to that pivot and like puts things smaller on the left, bigger on the right. And those are now, it turns it in to then, puts the pivot in the right spot, turns it into 2 smaller subarrays that you can then call quicksort on. All right, and due to the magic of recursion, because it's smaller, you can just assume those are getting sorted for you. You don't need any extra space like you do with merge sort, so you save on space as well. And that's it, that's quicksort. So let's talk about that. On average, it is n log n, all right, just like for merge sort. So let me show that to you. When I click this button, it's going to draw a line to show you what the pivot is, and it's going to make the things above the line, the bigger things, go on the right, and things smaller on the left. That's what partition does. So like, all right, that's a good pivot, right? It's right about in the middle. It's putting things that are bigger on the left, things that are bigger on the right, and things that are smaller on the left. And then it's recursing. So you see it highlighting just the things that the recursion is dealing with. And it's already sorted the left side. So it's working its way inwards, partitioning, doing the right thing. And then it's done. So that's quicksort in a nutshell. It will usually be n log n. It does have a bad worst case, because you are kind of like, you are very reliant on that pivot value, aren't you? So quicksort, if you pick a horrible pivot, if you pick like the biggest value to be your pivot, it's gonna split it up into like the biggest value and then the entire rest of the array, right? It's gonna be in the worst possible spot. And if you keep doing that, like you keep picking the worst possible pivot, like it's always the biggest value or always the smallest value, it's going to keep on chopping the array not into 2 equal sized pieces like you need to get logarithms, but into like one size that's about the same as like this is about size n again. Does that make sense? And so that's going to ruin this, and it's going to turn n log n, it's going to turn the log n back into another n. So in the worst case, if you keep picking horrible pivot values, it turns into n squared, all right, because of that. Like you are banking on that pivot. It needs to be a good pivot. Hopefully it's about in the middle of all the values that you're trying to sort right now. So that's the secret there. You can get around this. Usually you can always get this case of n log n by picking a random pivot each time. But you got to be very careful about that. Don't like always pick the first element or always the last element, because say your array was like perfectly out of order, you'll always be picking the worst possible one and it will split it up this way. I hope you see kind of that, what's going on there. Quicksort is, the code is a little weird looking, so do study that. It's in your book. There are also plenty of fun examples and drawings and animations online, plenty of YouTube videos about it. So I encourage you to watch those if you're interested in this stuff. This is like a very, very good thing to learn, all these different sorting algorithms, because they help you learn how to analyze algorithms. So like you look at the code and you can easily read off, oh, it's n log n, it's n log n, it's n squared. It has a different best case, it's linear. Like that's what you need to get good at. And that's what you're going to be forced to learn in CSCI 41. So it's good to start, all right? Good to start early. So yeah, I think that's what I wanted to say. That is searching, sorting, and complexity theory, and also some makefiles. Still in there somewhere, all right? So I think that is all there, and I will see you in the next one.